Hello guys.
This is our first example in steel connection design. So we're having now a 300 grade steel plates shown in the figure, and the type of bolts we're using is M28.8/S bolts. Uh, the maximum goal that we're calculating is for the N star, which is can be transported into this type of connection. So basically, as you can see here, that we're having some plates in tension. So we have the plates actually in tension because of the force. As you can see here, that this force from both sides are actually making a tension here, and this can break our bolts. So the plates actually in tension. We have also some bolts. The bolts actually in shear. So we have shear in bolts. We also having bearing and tearing in our uh, in our plates and bolts, which is the tearing means you're having a crack here with the bolt outside, and the bearing that you can see that this can expand. So, for example, if we're having this type of bolt is 20 millimeter. So basically, the DH or the hole of the ball of the bolt can be 22. It depends about the type of the diameter and the type of our bolt. So if this is actually a standard type, so with 20 less than 24, according to the quote, it's gonna be 22. So basically, this in the bearing can expand it. So instead of 22 millimeters, it might expand to 24 or 26, depends about the load. So this type of failure that we are checking. Also, we're going to check the combined shear and tension in our bolts. So let's start now by the blades and tension, how to check. All right. So what we're going to do first is to make analysis for our design. So this is actually, can say this is plate 1. Let's assume like we're giving it plate 1. And we have also here plate 2. You can see that plate 2 is 180 millimeters and plate 1 is the calculation of 40, 70, and 40 is going to be 135. So here we're having 150 millimeters. So 150 millimeters, and we're having 180 on the other plate. And you can see that we're having 4 bolts, and the edge distance, if you want to calculate the edge distance, so the edge distance is going to be this side, which is this side or that side, so it's 35. And we also have the thickness for the upper plate, which is this one. The upper plate thickness is equal to 12 millimeter, while the another one is equal to 10 millimeter. All right. What else we can get? That the the lab distance. The lab distance is actually the distance from the first ball to the last ball. So we're having here the distance from this side, this ball to this ball, which is giving here by 70. So this is just to extract the data for our analysis. So I think we are good now, so we can start by checking um, the tension in our plates. So the tension in plate, let's say we're going to check the plate 1. Plate 1 checking. So the tension is calculated by a load 0.9 NT. So
This is a maximum load that can be applied. So NT is actually calculated by the lesser. So we have to calculate two equations and see the lesser of them. So number one, we're gonna calculate AG, A gross, multiplied by Fy, and number two, we're going to calculate 0.85 KT AN multiplied by F ultimate. All right, so what is AG and AN? So AG, actually, we're going to cut a section in our plate. So section is, as I said before in the introduction, you have to cut the section in perpendicular to our M force. So we're having, this is the direction. So this is the direction of the force that we're having, the direction of our force, and the section must be perpendicular. So this is actually the section. All right. So with the A gross, we take the section without any holes in it. So we assume that this is going to be the section. So the section for A gross is going to be this one for the plate one. Okay, this is plate one. So we know that this one actually plate one, which is this smaller one. So 150, this is the distance, and you have here the thickness, which is on the top, is 12. So we have 12 millimeter and 150 millimeter. All right, and if we're talking about A gross, so this means we're talking all without any voids. However, when we're talking about AN, we need to subtract this A gross from the voids that we're having. And basically, how we're doing that, this is for the A gross. So AN is equal to A gross minus, you will have here the area of the voice, which is basically the number of bolts that you have in the section. Let's see the number of bolts. This is the number of bolts. Okay, yes, I'll make it clear. All right, so you're going to have the number of bolts multiplied by dh. Dh is the distance, the diameter of the void, and multiplied by the thickness. So what I mean by that is the AN is basically the same here. You have 150 and 12, but you're actually going to have two poles here. Okay, but in the section it's only going to see one pole, so you won't be able to see two poles because you're taking only the section. So this is going to be the section. All right, so this is for the first one, which is this one. If I'm taking this section here, I'm taking this section, or that section, it doesn't matter, they're all the same. So this is the first one, let's say this one, and then we have the second one, which is here. So basically, when talking about the AN, so it's going to be the A gross minus N, the number of bolts, which is 2. DH is not actually the diameter, so we're having here M20 means the diameter of the bolt is 20. But when we're talking about the DH, we're going to use the code to see how much is actually going to be this void, because if let's say that the diameter is M20, as I said before, so 20 millimeter is that diameter, but the DH, if it is a standard bolt, so it's going to be less than, and it is less than 24 as our case, so the DH is going to be 22. This is according to the standard code. So I'm going to show you the table later, but now just to extract information to see what is the difference between the DH and the diameter of the bolt. So there's different, and T is actually the thickness that we're having here is a 12. So basically what we're dealing with is we're taking the section as it is, this one, and we just subscribe this area. Just let me make it in other color. So we subscribe this area. All right. So this is AN. Now I'm going to solve it in an Excel sheet. All right, guys, this is my Excel sheet I created for calculating state connection capacity. So basically, I'm going to delete everything here. So all right, this is for welding. We don't have welding. So as we can see, in our example, we're having two plates. So one at the top and one in the middle. So I'm going to write the information here, and I'm going to go through our. All right. Sorry. Okay. So as you can see, let's go to plate one. We're having 150 millimeters and 12. Okay. So I'm gonna write this is 12 millimeter, and the plate in the bottom is actually 10. The length is 150, and then we having here is 180. So the edge distance, as I've already shown before, is 35 millimeters. So I'm gonna write 35 here and 35 here. So the overlap distance, the distance, as I said, from the first one to the last bolt. So this is actually the distance. So as I said here, 70 meters. So you have the first one here and the last one is here. So you calculate this distance is 70 millimeters. So I'm going back, I'm writing 70. I think yeah, 70. Okay, so the bolt type is actually 20. 20 is means 20 millimeter diameter. So I'm going to hit M20, M20. All right, it doesn't make sense. All right, because it's the same here, and over here is the same. So our bolt category is actually SB in the question. Let us check which type of bolt that we're using. Okay, according to the question, yeah. So 8.8/S. So writing 8.8. Number of bolts we're having 4, and the number of bolts in the section when we cut is actually 2 bolts. All right. The steel blade grade is actually 300K. So this is all the information. So let's go now to the process for checking the tension. So check the tension. So plates in tension, the law is actually the N star must be equal to 0.9 NT, and NT is actually the lesser of AG area gross multiplied by FY, or 0.85 KTAN multiplied by F ultimate. So let's start by AG. So as shown before, we have a section of for plate 1 on the top, you have a section of 180 for one plate. Okay, just let me check. All right, so we're having a 150 and 12 millimeter for the top, and for the bottom plate we're having 180 and 10 millimeters. So let's go back. So AG is going to be 1800, which is 12 multiplied by 150. All right, so this is actually the area gross. And for the FY we are using a grade of 300, this means 300 FY. So AG multiplied by FY is just multiplication, so you get this one, and this is actually the first one. So the first one you have to calculate is AG multiplied by FY. Now it's done. All right, which got 540 kilonewton. Now let's go to the another part. Another part is 0.85 KTAN F ultimate. So what is KT? KT in our case is actually going to be 1, and this is actually from here. So you go, this is the standard AS 400, 4100 reference if you want from Australian standard. You can check this one for how to calculate the tension in place. So this is actually how to calculate KT. So in our case, as I said before, if we have an symmetric shape, symmetric connection, so KT is going to be 1, and this is actually a simplified version. So KT is actually, this is from the code, and this is from another reference. So this is, you can see it's 1. When you have a symmetric shape, it's generally 1. When you have some kind of shape like this, or this one, a leg with an equal leg, like this side is actually equal to this side, so 0.85 is actually, you can go to the introduction. I've explained this kind of stuff. And if this is not equal leg, so 0.75. So as in our case, the blades is actually symmetric, and we're going to take KT as 1. All right. So KT, I think it is 1 from the table 7.3.2, as I've just shown here. This table is as a reference. And we go now for AN. So AN is actually equal to AG minus the number of bolts in a section multiplied by DH by the thickness of the plate. So the number of bolts in a section, I've already shown here that we're having 2, and the DH is calculated depends about the standard of the bolts that we're using and the diameter of our bolt. So to see what I mean, let's go to here. This is actually what I mean by DH. It depends about. So the standard, if we assume that we're not given in a question which type um, of balls that he's using, so we're gonna choose as a standard type. So for the standard type, the DH actually equal to depends about if the diameter is less or greater than 24. So for M20 means the diameter of our bolt is 20 millimeters. So we have DF here is going to be in this is going to be our case. The DH is going to be DF plus 2. So we have 20 plus 2 is going to be 22 millimeters. So this we're going to put here. The DH is going to be DF plus 2, as is already checked that we have that one. So DH is going to be 22. Means we're taking the 20 millimeters from our bolt type multiplied by 2 because it's less than 24. All right. So now we already got KT, we already got DH. So what we already missing is the F ultimate. F ultimate for FY 300 is 440. However, you can actually also check this from the table below. So we're going to check that. So you go here and you see what is our for our plates of 300. All right. All right, yeah. So this is actually, we're having 300, it means 440. This is actually the F ultimate, how much is it compared to that. So you can actually check from the table, or it's already basically 300 is 440. So we're using 440 for the F ultimate, and here you go. So that's now you already calculated just on 0.85 multiplied by KTA and multiplied by F ultimate. You got this one 508.64 kilonewton. Now the NT is actually going to be the lesser from both sides. So we're having to 540 and 508 from we got it. This is from using another equation, which is 0.85 kTA and multiplied by F ultimate. So the NT that we're using is going to be 508, and you have to use factors. N star is equal to 0.9 NT. So now you're having 457 for our N star. So the maximum load in our plate 1, which is the plate in the top, must be less than 400 something, 457. All right. So now we have to check. This is for you have two plates. So I've checked plate 1 and I've checked plate 2. So now I've already checked both of them. All right. So this is you're going to do the same. So you do for the plate 1 on the top, you calculate the same procedures, and then for the bottom, you do the same thing. So for the bottom, just to mention that when you're going to do the section, let's see. Now this is the section for the top one. For the bottom one, I'm going to draw it here. So for the bottom one, this is actually going to be your section. So 180 millimeters, and here is going to be 10. This is for the A gross. All right. For the AN, it's going to be the same, but you have to subtract these two voids, and all the procedures are going to be the same. So summarize up, you have the for tension is going to be for plate 1 and plate 2 because they're all the same. They're all having the same situation. So you calculate them and see that the maximum force applied in tension must be less than 428, which is after I calculate for the first plate, the top, and the second plate, and that's the result I got. So this is actually only for the tension. Now, after this one, I'm going to go for the balls and shear. All right, this is for the tension. It should be the M star should be equal or less than 428. And then I'm going to go for the shearing balls, for the bearing and tearing balls, for the combined action balls, and see which one is actually going to be my maximum force I can apply to this type of connection. All right. So we'll stop here and complete in our second section.